In a previous video, we talked about right triangle trig, and specifically, how do you solve a right triangle? So, given some information, can you find all the rest of it? And we did that using either or a combination of the Pythagorean theorem or just our standard trig functions, sine, cosine, and tangent, um, and some inverse trig. Now, if we didn't have a right triangle, we would have something called an oblique triangle. So an oblique triangle is simply a triangle that doesn't have a right angle on it. Now, there's a there's a right triangle on the slide here. So as a refresher of how you would solve a triangle like this, if you don't recognize that this is a 30, 60, 90 triangle and know how the side ratios work there, um, this would be 5 root 3 and this 5 root 3 over 3, and this would be 2 times that. So 10 root 3 over 3. Or you could just use our right angle trig and say, okay, with respect to that 30-degree angle, the cosine of the 30 degrees, because I have the adjacent, I want the hypotenuse, would equal 5 divided by e, and then e would equal 5 divided by the cosine of 30 degrees. Cosine of 30 degrees is root 3 over 2. So if you flip this, and you'll get these answers. Okay, uh, right, like I don't know. Hopefully that makes sense. It makes sense how to do the rest of that, right? It'd be 10 divided by root 3. Rationalize it. It's 10 root 3 over 3. Okay, and you could do the same thing with tangent if you wanted to find d. Now, this other triangle over here doesn't have a right angle. Like, we don't know that z, for example, angle z is right, and y certainly doesn't look like it's right. And so we can't just use sine right away to find, for example, x. Like, sine of 30 degrees is not x divided by y in this case. Cosine is not 5 divided by y. So there's got to be a way that we can solve these sides, and there is. And it kind of comes down to just sort of looking at an example here. If we have a triangle like this, let's give it some actual value so we can experiment here. It has to do with dropping an altitude. Okay, and what dropping an altitude means on a triangle is to choose a vertex, and this could be any vertex, and then draw a line that is orthogonal with the opposite side, or perpendicular with the opposite side. That green line I've drawn there from B down to from angle B down to side length B that intersects angle A and C. Sorry, side AC or side B. That is called an altitude. And then we can look at these two triangles that we've just created individually and come up with a way to solve. So let's do that. Okay, so we drop this altitude here and we call that the height of that altitude. Let's call it x. So if we're looking at the right triangle, we can say that the sine of angle A, and you would use, let's just use capital A, sine of A is equal to x, is x divided by c. So if I want to know something about x, x would equal, if I multiply both sides by c times the sine of A. Okay. Now if I look over here at this other triangle, and let's look at angle C, let's look at the sine of angle C. The sine of angle C is equal to x divided by A. And I already know what A is, right? So sorry, I already know what x is. It's c sine A. So I could substitute that x right here into right here, and I will get sine of C is equal to c times the sine of A divided by A. You still have that same A. If you were to now like, now it's up to you to whatever you want to solve here. You have the rest of this information, because we have angle A in this question is 50. We have angle C in this question is 70 degrees, and we also have angle B because all the sides in a triangle add up to 180. So if I have 50 and 70, that's 120. The remaining angle is a 60-degree angle. So I have everything I need here in order to solve this. Like, if, for example, right here, right, I have side length C, I have angle A, I have angle C, so I could just solve and get angle A. And so when you do that, I'm not sure what the answer is. Let's see, if we solve this for side A, we would multiply both sides by A, divided by, so it'd be A is equal to C times the sine of A divided by the sine of C, which is something. Let's see, 10 times the sine of 50 degrees divided by the sine of 70 degrees. That should be, I think, about 8.15. Okay, so side length A is 8.15, and we didn't use any special tools here. All we did was this concept of dropping at an altitude, and this, of course, can be generalized. So, generalizing this gives us something called the law of sines, and this is exactly what we did on the previous slide here. We just dropped it. We just looked at one triangle, looked at the other triangle, and now we're just using letters instead of numbers, and we get this relationship here. Now, if you had done that same process from any of the other vertices, so remember we chose B to drop our first altitude from. If we drop that altitude from C instead, then and do the same process but with these other two triangles that were formed, we'd have a similar answer. So what we do is we can apply that and say that this right here is the law of sines, and usually instead of angle A, angle B, and angle C, we have the angle variables are alpha, beta, and gamma. This kind of weird looking Y, it looks like a gamma. It's called gamma. Okay, so the ratio of the sine of an angle to the length of the side opposite the angle is equal for all angles in a triangle. That's what the law of sines is. Okay, special note here. Because the law of sines is just is equation that relates ratios, the reciprocals are also true. So, I mean, really, basically, like 1/2 is equal to 2/4, and this in the same way that 2/1 is equal to 4/2. So we can always make this statement, right? If and like the general term for that is, if you had A over B equals C over D, then B over A would equal to that's D over C. That's just a way we can do this. Why would we want to know both ones? Well, because if we have an unknown side length, it'd be better to use this one. If we had an unknown angle, it'd be better to use the other one. Just because of just algebraically, that's all. Just less manipulation. And then an extra note here, an extra extension, is that this ratio of a side length to the angle, so specifically A over the sine of like a side length divided by the sine of the angle opposite that side length, that is equal to the diameter of a triangle circumcircle. A circumcircle is just a triangle that has all the vertices of it's a circle that has all the vertices of the triangle on the circle. It's kind of neat. That's like not something that's going to come up in this class, but a cool little fact about the law of sines. Now, it's important to also know when can you use the law of sines. Well, you can use the law of sines in very many situations. It's extremely versatile, and it can really be used when you have two angles and one side of a triangle. Okay, that is the key way, because if you have two angles, you also, by the way, have three angles. Now, how do you know what, look at this angle, side, angle. How do we know what that is? Well, let's just draw a triangle real quick. And let's say I knew this angle and this side and this angle. If I read kind of clockwise, then this is an angle, side, angle. I have two angles on a side. If I had something like this where I knew this angle and this angle and this side, that'd be an angle, angle, side. In this case, like this would be an unknown, this would be an unknown, this angle would be an unknown. There is another scenario here where you could use the law of sines, and that's when you have something like this, where you have an angle, a side, and a side. Okay, and this is the problem with this here is that you have potential for something called an ambiguous case. And so you can totally use the law of sines here. And the thing is, you'd be using the law of sines to find probably an angle, most likely this angle, okay, or this angle, either one. And the issue is that you're going to be, when you use the law of sines to find an angle, you need to use the inverse sine function, right? And when you use the inverse sine function, there are some limitations to the output. So you need to be really careful here. There's all kinds of interesting analysis that you have to do, which we'll get into, about the ambiguous case, where you have a potential for two triangles that can meet the givens of a problem. And we'll get more into that. But for now, we're going to be using the law of sines on problems that just you can straight up just use the law of sines on with no issues. And keep in mind that there's another tool called the law of cosines that we don't know yet. And the law of cosines is actually kind of more versatile. It always sort of works primarily because of how inverse cosine works. Okay, so anyway, let's look at a problem here. Here's a problem where we have an angle, and a side, or a side angle, angle. So this is prime for using the law of sines. If we want to know what angle alpha is, well, that's really easy because all the angles inside of a triangle add up to 180. So if we subtract 95 and 45, that's 140. So this angle here is 40 degrees. So boom, that's really easy. Okay, now how does the law of sines work? Well, let's say, for example, I want to find side length B. Well, I know that so if I set up this ratio, so B divided by the sine of 45 degrees is equal to, now choose any other thing. Choose the one that you know. So in this case, I have 5, I have the 95, I have the 5. So that's going to be equal to 5 divided by the sine of 95. So I just need to solve this for B. So B is equal to 5 times the sine of 45 degrees, which is root 2 over 2, but it doesn't matter because I don't know what the sine of 95 degrees is, like off the top of my head. So what does this equal? Well, let's just do it real quick. So we've got 5 times the sine of 45, 5 divided by the sine of 95. Enter. It's 3.45. So side length, that was B that we found, was 3.55. Cool. Now, what is A? Well, we could do the same thing. Now we want to find A. So we're going to use A and 40 degrees. A divided by the sine of 40 degrees is equal to, then use this one again because it's exact, right? We don't want to use this 3.55 that we just found because we rounded it. So use the same ratio we had that was all given to us. Yeah, and then that's going to be A is going to equal 5 times the sine of 40 degrees divided by the sine of 95 degrees. I expect this one to be a little shorter because the sine of 40 is a little less than the sine of 45. So let's just actually do that. We're going to change that 5 to a 0. And we get 3.23-ish. Right, so A is 3.23. 3.23. So there we just solved that oblique triangle using the law of sines. Okay, next one we have here, if we read this kind of go around clockwise, let's see, we have an angle, a side, and an angle. That's a law of sines thing we can do. So first of all, let's find that missing angle. That's always the easiest thing to do. 180 minus 85 minus 30. So that's 180 minus 115, which is what, 65? So beta is 65 degrees. Okay. Then let's find A. So again, we want to find A first. Then we say A divided by the sine of the angle that's opposite side length A, which is the sine of 50 degrees. That's going to be equal to, and then use the information we know that's for sure exact. So we have this side of 3. So that's going to equal 3 divided by that angle opposite, which we found it was 65 degrees. So sine of 65 degrees. If we now just solve for A, we're going to have A is equal to 3 times the sine of 50 degrees divided by the sine of 65 degrees. Let's do that. So 3 times the sine of 50 divided by sine of 65. Enter. It's 2 point, so A is 2.54. Okay, now if you want, you can pause the video here. Hold on, did I do that wrong? Sine 2.543. Did I add 3? What do we do? 85 minus 30. Oh, I wrote 30, but I meant 50. I'm sorry. This is all messed up. This should be 35 degrees, right? This isn't right. So that's 35 degrees. That means this is 35 degrees. This is 35 degrees. And when you plug it into calculator, what you're going to get is 3.25. Now, I'll let you pause the video here and solve for B. Side length C. So we're going to use C divided by the sine of 85 degrees is equal to 3 divided by the sine of your 35 degrees. And pause the video and I'll write the answer. So the answer should be 4.23 there. Okay, this is not a degree. These are both side lengths. All right, so that's using the law of sines. Let's do one more problem here. Okay, here these are the givens, and this is the same kind of format that we had with right triangles where we're just given a standard right triangle and the labels aren't drawn directly on it. We're just given these values. So we can put these things right on it. So 40 degrees right here, beta is 20 degrees. That means that gamma, right, is going to be 120 degrees. And now we have side length A is 2. So we just say, all right, what if we want, well, gamma is 120, we already know that. If we want side length B, then we have B divided by the sine of 20 degrees is equal to, and then remember, use the side we're given, so 2. 2 divided by the sine of 40 degrees. Or if I want to find B, B will be equal to 2 times the sine of 20 degrees divided by the sine of 40 degrees. And if we want to find whatever that is, we'll find it in a second. C, C divided by the angle opposite, the sine of the angle opposite of C, which is 120, sine of 120 degrees is going to be equal to, and then just use the same ratio again, 2 divided by the sine of 40 degrees. So C will be 2 times the sine of 120 degrees divided by the sine of 40 degrees. So let's see if we do this, if it makes sense. Okay, so remember what we have here. We have the situation where we've got an angle, we have an angle side angle. Okay, so what's the answer going to be? Let's check. Let's do the calculator here. B would be 2 times the sine of 20 degrees divided by the sine of 40 degrees. Okay, so that's 1.06, 1.06 for B, right? 1.06. Okay, now let's do a thought experiment here. If this angle is 20 degrees and this angle was 40 degrees, we should expect the side that's opposite the smaller angle, so in this case side length B, we should expect that to be less than side length A, because angle A is twice as fat as angle B. I know it doesn't look like it in the triangle, but that's what we have for our values. And by the same reasoning, this angle, the side that's opposite our biggest angle, which in this case is actually obtuse, 120 degrees, should be way bigger than A or C. So C should be by far the largest side. So let's see what happens just to make sure it is when we do this. 2 times the sine of 120 degrees divided by the sine of 40 degrees. Nope, that's 40. Sine of 40 is equal to 2.69. Oh, so we're still in highlighter mode. 2.69, yes. So that should make sense. It's significantly larger than the other triangles. Cool. All right, now let's do the last problem. Last problem is a word problem, applications. So this is part of the reason why law of sines is super important. When you're an engineer and you're doing stuff like calculating angles on trusses or side lengths and different things, you really do use the law of sines for stuff like this. This guy's a surveyor. He's looking through an instrument and he's got these angles. And he's looking for the distance. He knows the distance between grandma's house and the nursing home is 150 feet, and he sees these two angles. So we know that this third angle, because all the sides in a triangle add up to 180, must be 30 degrees. Okay. So how far is it from where he is to grandma's house? So we'll call that x. And then the other distance, how far from where he is to the nursing home, we'll call that y. So we just set up the law of sines here. If I want to find x is to the sine of 60 degrees as 150 feet is to the sine of 30 degrees. Okay, so if we do know these values because they're unit circle values for 60 and 30, so happens. Sorry, it's not, it shouldn't be, right? It's 40 degrees, not 30 degrees. I'm sorry. We don't know that. It's having a hard time adding up to 180 today. Okay, so what is this? Well, solve for x. Okay, x is equal to 150 times the sine of 60 degrees divided by the sine of 40 degrees. The other one, if we want to solve for y is to the sine of 80 degrees It's deleting for some reason, as 150. 150 is to the sine of 40 degrees. 40 degrees, okay? So y is equal to 150 times the sine of 80 divided by the sine of 40. All right, and if we calculator these real quick, 150 times the sine of 60 divided by the sine of 40 is 202.1 feet. Okay, now do we expect, based on our discussion in the previous problem, did we expect the distance to the nursing home to be farther or shorter than the other distance of the 202? We would expect it to be longer because the 80-degree angle is greater than the 60-degree angle. Let's see if that's true. So 150, I'm having a problem with the calculator here. 150 times the sine of 80 divided by sine of 40 is 229.8. So it's 229.8 feet. So it is a little farther. So it's good that we found that. All right. So that is using the law of sines. The law of sines, again, is very versatile, but there are some situations where, although we can use it, you have to really know what's going on in the problem to trust the answer. And that, again, is due to if you're using the law of sines to find an angle, especially if that angle you're trying to find is obtuse potentially, there's an issue. Okay, so we are going to get into that in the next video when we talk about the law of sines. Oh, sorry, the law of sines. Oh, we just did that. The law of cosines and this ambiguous case, the angle side right triangle. Some teachers will call that the side angle right triangle. I think that is a lot less funny, and you'll discover the reason why for that if you have not already picked up on that in the next video.